Hello, so today is the first in a series of videos about amount of substance. So we're going to be looking at the first one today, which is about the mole and Avogadro's constant, or the Avogadro number. So our checklist, so by the end of the session we should be able to recall the definition of the mole, calculate the number of moles, or it's sometimes called amount of substance, and use Avogadro's constant to calculate the number of particles or the mass of one particle. So we often use words to describe money. We might say we might have a dozen bananas or a dozen eggs or a dozen apples or something. We just mean 12. We might have a pair of shoes. We mean 2. We might have a ton of cash. It means 100. These are just words that we use to represent number. So to a chemist, a mole is just a number. It's just a quantity of stuff that you have. So if I've got a mole of something, that means I've got a certain number of particles. It's an amount, it's a quantity. IUPAC, who are the International Union of Pure and Applied Chemistry, define the mole as being a unit of amount of substance, i.e. how much stuff there is. 1 mole contains exactly 6.022 14076 times 10 to the 23 elementary entities or particles. This number is a fixed numerical value of the Avogadro constant Na when expressed in mole to -1 and is called the Avogadro number. 1 mole of a substance has Avogadro's number of particles in it, and the Avogadro constant or the Avogadro number is 6.022 times 10 to the 23. So that means if I've got a mole of anything, I have 6.022 times 10 to the 23 particles. So if I had a mole of water, there'd be that many particles in it. If I had a mole of pound coins, I'd have that many pound coins, which would be an awful lot. It's a huge number, okay? That's how big it is. It's massive. It's gigantic. It's such a huge number. If I had a mole of donuts, then it would cover the Earth to a depth of 5 miles. So the whole surface of the Earth would be covered by 5 miles of donuts. That's an awful lot of donuts. It's a huge number. So how can we calculate a mole? There are several ways. The most basic way is we can do the mass divided by the MR. Now the units for moles is just mole. The unit for mass is grams. It always has to be in grams, otherwise you're not calculating a mole. The relative formula mass, or the MR, is in grams per mole, and the symbol equation for this is N equals M over MR. Commit this to memory. You will use this an awful lot during chemistry. So 1 mole, or an amount of a substance, is the relative formula mass or the relative atomic mass in grams. So what that means is for carbon 12, where the relative atomic mass of carbon is 12, in 12.0 grams of 12 carbon, I have 1 mole of atoms, or Avogadro's number of atoms, 6.022 times 10 to the 23. So in 1 mole of anything, I have this number of particles. So an example calculation, the real basic calculation, is how would we calculate the number of moles of 2.20 grams of carbon dioxide. So the first step is we need to work out the MR of CO2. Okay, I've put a little bit of the periodic table here. Remember, it's the relative atomic mass, so it's the top number we need. So this tells us we've got 1 carbon and 2 oxygens, so it's 12, plus we find oxygen, which has a relative atomic mass of 16, and there are 2 of them, which equals 44. So then to work out moles, we do mass over MR, which is 2.20 divided by the MR, which is 44, which will give us an answer of 0.0500 to 3 significant figures. Example mole calculation 2. Calculate the mass of 1 times 10 to the -3 moles of H2SO4. So the first thing again is we need to work out the relative formula mass of H2SO4. So this tells us that there are 2 hydrogens, 1 sulfur and 4 oxygens. So we find the relative atomic masses of them. So hydrogen is 1 and there's 2 of them. We're going to add that to sulfur, which is 32.1, and we're going to add that to 4 lots of oxygen. Each oxygen is 16. That gives us 98.1. Okay, now our equation is N equals M over Mr. This is currently how to calculate the moles, so we need to rearrange this equation. So to work out the mass, we do mass equals N times Mr, or a helpful way sometimes you can remember it is mass is Mr. Moles. Okay, and that will give you 1.00 times 10 to the minus 3 times 98.1, and that will give you an answer of 0.0981, and that's grams. Using Avogadro's constant. So Avogadro's constant can give us 2 useful things. It can allow us to calculate the number of particles, and it can allow us to calculate the mass of one particle. Remember, 1 mole of anything has Avogadro's number of particles, which is 6.022 times 10 to the 23. So, converting those into equations. So to calculate the number of particles, you simply times the moles by Avogadro's constant. So for example, if I wanted to know how many particles there were in 1 mole, I would just times that by Avogadro's number, and that would very sensibly give me 6.022 times 10 to the 23. If I have twice the many particles, so I've got 2 moles, then it was going to give me 12 times 10 to the 23. That's a 3, not a 5, etc. To calculate the mass of one particle, and that could be a molecule, it could be an ion, it could be anything, we need to divide the relative formula mass, or if it's an atom, the relative atomic mass or the isotopic mass, divided by Avogadro's number. So essentially, you're going to do the relative formula mass divided by Avogadro's constant. Okay, let's look at some examples. So example 1, we're going to calculate how many copper atoms there are in 0.5 moles of copper. Okay, so we're going to use the first of the 2 equations that I gave you, which is the number of particles equals moles times Avogadro constant. What I will say is just a side note here, I'm going to use L to represent the Avogadro number or constant. Depending on your exam board will depend on the symbol they give it. What I've noticed is OCR A and B salters use Na to represent Avogadro constant, which is actually the same as our UPAC, and AQA and EDEXCEL use the symbol L. So I'm going to use L, but Na could be the same. What is common to both exam boards is the number, which is 6.02 times 10 to the 23. So we do 0.5 times 6.022 times 10 to the 23, and that will give us 3.011 times 10 to the 23 atoms. Okay, so that's how many copper atoms there are in 0.5 moles of copper. So we're going to look at 2 more examples. These both use the second equation, which is to calculate the mass of one particle, where we do the relative formula mass or the relative atomic mass divided by Avogadro's constant. Okay, so calculate the mass of a 35 Cl chlorine atom. So the mass number of this is 35. So we're going to do 35 divided by Avogadro's number, which is 6.02 times 10 to the 23, which is going to give us the mass of one chlorine atom, which is 5.81 times 10 to the minus 23 grams. Second example is to calculate the mass of a water molecule. Well, a water molecule is H2O, so our first job is to calculate the Mr of water. So hydrogen is 1 and there's 2 of them, and oxygen is 16. Those are the relative atomic masses, which gives us a relative formula mass of 18. So then we're going to do 18 divided by Avogadro's number, which gives us the mass of one water molecule, which is 2.99 times 10 to the minus 23 grams. Okay, let's have a look at a few exam questions. Question 1. Calculate the number of europium atoms in 0.0019 grams of europium. Give your answer in standard form and to an appropriate number of significant figures. Okay, so I've pulled the europium atom out of the periodic table and it's got a relative formula mass of 152. Thinking about standard form, so that's going to be times 10 to the something and an appropriate number of significant figures. Well, these are the two values that we have. We need to give it to an appropriate number of significant figures, which is the least number of significant figures of these. So our final answer is going to be to 2 significant figures. I always recommend identifying that first before you start the question, so then when you come to your final answer, just look up and check, have I given it to the right number of significant figures and have I given it in standard form. So job 1 is we're going to calculate the number of moles of europium, okay, which is mass over relative formula mass, or in this case it's relative atomic mass, so it's 0.0019 divided by 152, and that is going to give you 1.25 times 10 to the minus 3 moles. Step 2 is to calculate the number of particles. So we're going to be using the first equation, which is the number of particles is moles times Avogadro number. So that's going to be 1.25 times 10 to the minus 3 times Avogadro's number, which is 6.022 times 10 to the 23, and that is going to give you an answer of 7.5 times 10 to the 18 particles. Remember, 2 significant figures, standard form. Let's have a look at the mark scheme. So the first mark is for calculating the moles, which is 1.25 times 10 to the minus 5. And the second mark is for 7.5 times 10 to the 18, given to 2 significant figures and in standard form. Question 2. This is a multiple choice question. How many electrons are removed from 2.02 times 10 to the minus 2 grams of neon atoms to form neon plus ions? So the equation, so neon is forming neon plus ions plus E minus. So because it's a 1 plus ion, we're removing 1 mole of electrons for each mole of neon atoms. So our first job is to calculate how many moles of neon there are, because we know the mass of neon. Then we can work out how many moles of electrons we've removed, and then we can work out how many electrons we've removed. So the moles of neon is mass divided by relative atomic mass, which is 20.2, which is going to give us an answer of 1 times 10 to the minus 3. So remember, this equation shows us that 1 mole of neon makes 1 mole of electrons, or rather we remove 1 mole of electrons to form neon plus, but we don't have 1 mole of neon, we've got 1 times 10 to the minus 3 moles of neon. Therefore we're going to have 1 times 10 to the minus 3 moles of electrons. So to work out how many electrons, we do 1 times 10 to the minus 3 times Avogadro's number, which equals 6.022 times 10 to the 20, which is option C. Okay, exam question 3. Now this is starting to get a little bit trickier. So, how many protons are there in 6.0 grams of nitrogen gas? And they've given us Avogadro constant. I've just pulled this out of the periodic table, just so you can see where I'm getting the numbers from. The first thing that they've not told us, which is incredibly important to work out, is that nitrogen gas is N2. Nitrogen is a diatomic molecule as a gas, so it's N2. So, how many protons are there in 6 grams? So our first job is to calculate the moles of N2, Then we need to calculate how many protons there are in N2, and then we need to work out how many protons there are in the N2 in the 6 grams. So to calculate moles of N2, we're going to do mass divided by relative formula mass, which is MR, which is 6 divided by 28. Remember, it's N2, so it's 6 over 28, which equals 0.214 ... Leave the full number in your calculator. Okay, so the second step is to work out how many protons there are in an N2 molecule. Okay, so we can see from the number here, the atomic number of nitrogen is 7, therefore a nitrogen molecule has got 14 protons. Okay, but we've been asked to work out how many protons there are in 6 grams of nitrogen gas. This is only one molecule of nitrogen. Okay, so we can work out how many nitrogen molecules there are by doing Avogadro's number times the number of moles, which is using the first equation. Leave that number in the calculator. That is how many nitrogen molecules there are. So if we multiply that by 14, which is how many protons there are, that will tell us how many protons there are in 6 grams of nitrogen gas, which is 1.8 times 10 to the 24. Remember, leave this full number in your calculator when you're doing the steps. 1.8 times 10 to the 24 is option C. So the examiner's report on this question says that the most common answer, D, was incorrect, and that was a value that was twice the correct answer. So I suspect what people have done is they've used the relative atomic mass of nitrogen being 14 as opposed to the relative formula mass of a molecule being 28. Question 4. Which sample contains the most molecules? There's quite a lot of work to do here for just 1 mark. Okay, so we're going to look at A, B, C and D separately. So A just tells us how many molecules there are, so that's easy. We don't actually have to do a calculation there. There are 2.10 times 10 to the 22 molecules. B, 1 gram of oxygen, which is O2. Okay, so the first thing we need to do is do 1, work out the moles, which is mass over MR. So that's 1 divided by the MR of oxygen, which is 32, because there's 2 of them, and each one is 16, which gives us the moles. And then we need to times that by Avogadro's number to work out the number of molecules, which gives us, and I'm going to give 1.88 times 10 to the 22. Okay, so that's how many molecules in 1 gram of oxygen. C, 65.0 milligrams of hydrogen. So the first thing we need to do is convert 65.0 milligrams into grams. So I divide that by 1,000, which gives me 0.065 grams. I then need to divide that by the relative formula mass of hydrogen. Remember, it's H2. Each hydrogen atom is 1, so I'm going to divide that by 2. Then I'll times that by Avogadro's number, which gives me the number of molecules, which is 1.96 times 10 to the 22. D is, we've been told the number of moles of ethane, so we don't need to work it out. So we can simply do number of moles times Avogadro's number, 23, which gives us 1.81 times 10 to the 22. So we now have all the molecules. We just need to see, we now have how many molecules there are in each of these. We just need to see which is biggest. 2.1 times 10 to the 22, 1.88 times 10 to the 22, 1.96 times 10 to the 22, 1.81 times 10 to the 22. So A, the one we actually didn't have to work out, is therefore the answer. So it's A. Examiner's report says students found this question challenging. 38.8% correct, possibly from a lack of familiarity with using the Avogadro constant. Well, hopefully you won't have that lack of familiarity now. And that brings us to the end of this first video on amount of substance. So hopefully you can recall Avogadro's constant L or Na, depending which exam board you use, calculate the number of moles or the amount of substance using masses and relative formula masses, and using Avogadro's constant to calculate the number of particles or the mass of one particle. Thank you very much for listening. I hope that was helpful.